Hello Math 3680 students. Let's begin Lesson 4. Lesson 4 and Lesson 5 will cover Chapter 3 of our textbook, Discrete Random Variables and Probability Distributions. By the way, Chapter 4 is Continuous Random Variables and Probability Distributions. And that's going to be covered by Modules 6 and 7 according to my mathematical notebooks. In other words, you're going to stay in this topic of random variables and probability distributions for quite a while, and you got to know what they mean. What is a random variable? What is a probability distribution? What is a discrete random variable? And finally, what is a discrete probability distribution? You got to know all those. So let's begin. What is a random variable? Here's a definition. A random variable is a real function that assigns a real numerical value to each outcome of the sample space. And the random variable is called discrete if the image set is discrete. For example, if the random variable takes, say, 5 different values or 200 different values, and infinite, then of course is discrete. If it takes only integer values, things like those, they're all discrete. Now, if it covers entire closed interval, for example, then that's a different story. That cannot be discrete. Here are some examples. An urn contains 5 red balls, 3 green balls, and 2 blue balls. Therefore, the sample space is RGB. Now, I don't see any numbers there, so the mathematics we can do to the sample space is rather limited. I do have some number here, 5, 3, and 2 out of total 10. So I can do some computation and some mathematics on probabilities. But as for the outcomes, nothing much. However, if I assign some numerical values, then I can do some further mathematics. Let's suppose this random variable x. Select a ball at random, and if it is red, then 0, green, 2, blue, then is 3. Here's another example here. In random variable y, select the ball, and if it is red, then negative 1.5. So you pay $1.50, and then green, then you earn 50 cents, and blue, then you earn $1. Okay, so much for random variable y, and here's a third random variable z. This time, either red or green, then you must pay $1.25, and if it is blue, then you win $4.75. There can be many other games, but as for examples, those are sufficient, and let's do some mathematics with these. First example, what is the probability of capital X less than or equal to 2. So this one is about random variable x. And let's consider the event where this capital X is less than or equal to 2. So no red, because 0 does not belong to this. 2 is okay. 2 is less than or equal to 2. So yeah, that's okay. And 3 is not okay. As a matter of fact, 0 was okay. Originally, I have thought about the other direction. Sorry about that. 0 is okay. 0 is less than or equal to 2. That's okay. 2 is equal to itself, so that's okay. 3, that's no good. And yes, this is a probability. So red or green. So we have this probability. So red or green, if you express like this, then this is just logical expression, nothing more. But that's equivalent to this algebraic expression. So using random variable, you can rewrite the condition for the sample space and outcomes in an algebraic expression. That's what this random variable does. Here's another example. The probability that random variable y takes value strictly greater than 0 but less than or equal to 1. Alright, strictly greater than 0, so no red. Green and blue are both okay. 0.5 is strictly greater than 0, so that's fine. And then 1 is equal to itself, so less than or equal to itself, so that's okay. And therefore we get this computation, either green or blue. Now how about the third game? Z is equal to negative 1.5, so it's going to be either red or green. So we have this. By the way, as far as this game Z is concerned, as far as this random variable Z is concerned, there's no distinction between red and green because they're the same. For other random variables, of course, there is difference between red versus green, but for Z, no distinction. Here are some further examples of discrete random variables. Roll a die and number of eyes. Okay, 1 through 6. Okay, that's discrete. Any finite is discrete. Toss a fair coin and some numbers, and I want you to, get some complicated numbers because I encounter some students that the random variables must produce something really simple. But no, not really. I mean, pi or e, they can be really bad, but still, there are only two outcomes, so this is discrete. All the examples we considered previously, those are discrete random variables. And here's one more example. This one is called Poisson random variable, and it can take any non-negative integer value. So it's not finite, but still this is discrete. Okay, so much for section 1 of this notebook. Let's see. Yes, I have plenty of time, so let's go over to section 2 and let's discuss at least some of this section 2, discrete probability distribution. Let's take care of some terminologies. Let's begin with something called the probability mass function, defined like this. Given discrete random variable x, we can define a certain real function small p like this. P of small x is the probability that's random variable capital X taking the value of small x. Too many x's, so it can be a little bit confusing, I'm afraid. But we're going to talk about a little bit more detail and examples of it later. For now, let's just postpone all those detail and let's focus on just one thing. This is probability of a certain event. So this is a well-defined quantity. And let's just move on, at least for now. Next, a cumulative distribution function. Again, another real function, and that's determined by the probability of this random variable capital X taking the value less than or equal to small x. Again, we are not going to go through the detail here yet. Yes, we will, but a little bit later, and we're going to dig really deeper. But for now, let's focus upon just one thing. This is given by a probability, given by this condition. So it's a probability of a certain event. So it's a well-defined quantity. So let's leave it at that. Mass function, here's a well-defined quantity. Cumulative distribution function, again, well-defined quantity. Now, what is so-called a discrete probability distribution? Here's my description. A discrete probability distribution of a discrete random variable refers to either its probability mass function, PMF, or cumulative distribution function, CDF, or both of them put together. A little bit confusing? No, not really, because it'll turn out that if you know PMF, you can determine CDF and vice versa. If you know CDF, then you can find PMF. So even if it is just either one of either PMF or CDF, it's okay because we automatically know the other one as well with some effort. So it's okay to describe the probability distribution as either any one of those two. Or, of course, both of them put together. That's called a discrete probability distribution, and that is my own description. Our textbook author does not really make an effort to explain what this is. And if you go to some internet source or something and try to find out what is a distribution, then you're going to encounter something really intimidating. So I'll just leave it at that. Instead, let me show you something just for fun. And this is an attempt by a textbook written by Jason and Kubi. It's an elementary textbook. And I mean, I like this textbook, and I have a lot of respect to these people who wrote this great textbook. But still, this description is possibly the worst attempts to make any kind of clarification on any mathematical concept anywhere I've ever seen. Stop the playback and read through. Does it make sense? It's an explanation of probability distribution, and here goes the explanation. A distribution of the probabilities associated with blah, 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 blah. So what is this? Simply change the order of two words and suddenly it becomes understandable? I mean, the description of probability distribution is a distribution of the probabilities and some even more confusing terms. Come on, this is possibly the worst I've ever seen. And attempt by Sullivan's textbook is not much better either, as a matter of fact. And our textbook by J. DeVore wisely attempts to skip that attempt. And my decision is to just refer to either the mass function or the distribution function, or both of them put together. So, alright, what is probability distribution? Yeah, we have a good description. Probability distribution means either PMF or CDF or both. Alright, I am to a certain degree satisfied with this explanation on probability distribution, but maybe not you guys, because as an explanation of this new concept, probability distribution, you ended up encountering two more new concepts to clarify. But that's what we'll have to do. So, okay, let's go ahead and begin. Alright, what is the probability mass function? No, excuse me, sorry. I'll stop here, right here. And then we'll discuss the probability mass function and cumulative distribution function along with those examples in a separate video. I guess I'd better stop here. I have another long story coming, so let's stop here.